Hi, this is Vigyan Singhal. Today I'm going to talk about formal verification as we have applied to networking designs. Now, networking designs are typically very large chips. They have a lot of switches in them. And in this picture, I show a bunch of switches where traffic comes in from many different ingress ports on the left side, goes through MAC layer functionality, forwarding engine, address filtering, and then buffering and quality of service based routing, going to a crossbar, and eventually gets destination routed to a correct switch and goes back on the egress side, on the left side. What's very typical about these blocks is that a lot of these blocks in this picture are data transport blocks, not data transform blocks, which makes it very applicable to formal verification, despite some of the challenges I'm going to talk about in the next slides. The challenges are because the data width is really very large. It could be hundreds of bits or bytes. The designs may be handling and supporting many different ports. 48, 64, 72 ports are typical examples. The designs may have very, very large SRAMs, hundreds of thousands of millions of bits, may have implemented linked lists and permutations, data structures which are very common in some designs, but make it very hard for formal verification to converge. What becomes very effective for designs like this is the use of symbolic variables to implement symbolic checkers, where these variables could be varying over different port numbers, different data bits, token IDs. And on top of this, we can also apply abstraction models such as reset abstraction model, counter abstraction model, memory abstraction model, or linked list abstraction models, some of which we'll show in the examples in the following slides. A very well-known technique, the wolf per sequence abstraction verification, is also useful in such designs. We've been verifying networking designs for a long time because formal verification is very useful and applicable and complements simulation very well. Many of the customers are shown here. With Barefoot Networks, we published a press release a few weeks ago where we described how complex their design is. And despite the complexity, with the use of formal verification, it can be verified completely and exhaustively by breaking the verification problem into various blocks. I'm showing some examples now. Here's a multicast crossbar design. It's supporting 8 different clients on the left side, 8 targets on the right side. And because you have 8 clients and targets, there are 64 possible paths. One naive approach is to model 64 different FIFOs, modeling all the inputs that are coming in from a given client going to a specific target. But you can do much better than that by using symbolic variables and model any arbitrary symbolic client on the left side, symbolic target on the right side. And in one run, you can verify everything with only one FIFO in your checker. On top of using symbolic variables, you can also use a counter abstraction model. Here we have a packet statistics module. The symbolic variables are used to pick any single statistic out of the hundreds of statistics you may be designing and verifying over different memories and different banks and different ports. Even after you pick a specific counter, you still want to expose deep corner cases when the counter is saturated, and if it's a 32-bit counter, it may take you forever to saturate the counter. But by using a counter abstraction model, you can reset the design from any possible state of the counter and verify it completely exhaustively. World abstraction model is very useful to verify that sequences of data packets that go in don't get dropped, duplicated, corrupted, or reordered inside the design. And by just using 2 kinds of packet 0 and packet 1, I can verify this completely. Packet rewrite module is taking a packet, fragmenting into cells, and then doing some modification on each cell. It could be even inserting or replacing or removing bits or bytes inside the cell. And it ends up making these cells not so regular, and the cells may need to be reformatted again. And what happens in such design is that verification becomes very hard, both with simulation and with formal verification, because any single bit, depending on the reformatting that happened, can end up anywhere on the output. So one classical technique for that is to watch a specific bit which is coming out of the design and then trace its way back and make that bit symbolic. And then on top of it, inside the design, as well as in the checker, you can make an abstraction model on the memory. And instead of modeling the entire memory, you could be watching just one bit at a time. And that's the memory abstraction model we talked about. The tag allocator block manages a set of tags. It could start with an empty list or a full list. There are a bunch of requesters which are asking for new tags. The tags are being returned asynchronously by a bunch of returning agents. And there are many requesters and returning agents which are all operating asynchronously. The challenge with this design is that in this specific design, there were 8 different linked lists, purely because the design was working with very strict latency requirements with high performance. And if one linked list was busy, it was using a different linked list at the same time and supporting multiple requests and returns. It was referencing a next pointer memory, which was a very large memory, and the challenge was to not expose this large memory to the formal tool. And the way to do that was to pick a symbolic tag, make a state machine representing just 4 different states with just 2 flops, representing whether that particular tag is any of the linked list or not, if it's the tail of a linked list, if it's in the middle of a linked list, or if it's at the head of the linked list. Once you have the state machine, what you can model is constraints which implement the abstraction model. And one example of a constraint is that if you're at the tail of a linked list and the occupancy of the linked list is only 1, and if somebody requests the next pointer and Q is at the tail, then the return must be Q. If you're not in the linked list, then the return cannot be Q. And similarly, you have other constraints to completely model the abstraction model. Those are some of the examples that are very useful to verify networking designs. And I showed you some techniques which are making such verification very efficient. Thanks.